Welcome to Calm Science Nights. I'm so glad you're here with me tonight. Whether you're winding down after a long day, seeking comfort in the rhythm of nature, or simply letting your mind drift like a boat on calm waters, you've found the perfect place to be. Tonight, we're embarking on a peaceful journey together, a journey to understand one of Earth's most mesmerizing phenomena, something you've probably seen countless times but perhaps never fully contemplated. We're going to explore ocean waves. So take a deep breath with me. Listen, if you can, to the imagined sound of waves gently lapping at a shore. Let your shoulders relax, your breathing slow, and allow your mind to drift with me across the vast, rhythmic waters of our world. Close your eyes and picture the ocean. Endless waves rolling toward shore, one after another, in a pattern that seems both random and perfectly ordered. Waves have been doing this dance for billions of years, long before humans walked the earth, long before there were shores as we know them. And here's the question we'll gently explore together tonight. What makes waves move? What invisible forces choreograph this eternal ballet of water and energy? Let's begin our story where all ocean wave stories truly begin, not at the shore, but far out at sea, where the wind first touches the water's surface. Our journey starts with something so simple, so everyday, that we rarely think about it: wind blowing across water. This is where most ocean waves are born, in a process that's been happening since Earth first had oceans and an atmosphere to create wind. Imagine, for a moment, the surface of the ocean on a perfectly calm day, rare as such moments are. The water is smooth, almost like glass, reflecting the sky above. Then a breeze begins to stir. At first, it creates the tiniest ripples, barely visible wrinkles on the water's surface. These small disturbances are called capillary waves, and they're held in their tiny form by surface tension, the same force that allows water striders to walk on water. Surface tension is the tendency of water molecules to stick together, creating a kind of invisible skin on the water's surface. For the smallest waves, those less than about 1.7 centimeters in length, surface tension is the dominant force, pulling the water back to flatness almost as quickly as the wind disturbs it. These capillary waves are delicate, fleeting things, dancing across the surface like whispers. But as the wind continues to blow, something remarkable happens. The wind doesn't just slide smoothly over these ripples, it catches on them. The tiny waves create a rougher surface, and this roughness allows the wind to grip the water more effectively, transferring more of its energy into the motion of the water. The ripples grow into larger waves, and once waves reach beyond that critical length of 1.7 centimeters, gravity becomes the dominant restoring force rather than surface tension. Now we have what are called gravity waves, the waves we typically think of when we picture ocean waves rolling toward shore. This process of wave generation is surprisingly complex and was one of the great puzzles of oceanography for centuries. Scientists in the 1800s struggled to understand exactly how wind energy transfers to water. The breakthrough came gradually, with contributions from many researchers, but a key insight emerged in the early 20th century. Waves grow because of a kind of resonance between the wind and the water surface. Here's how it works. As wind blows over a wave, it creates slightly higher air pressure on the windward side of the wave, the side facing the wind, and slightly lower pressure on the leeward side. This pressure difference pushes the wave in the direction the wind is blowing and helps it grow taller. The larger the wave becomes, the more effectively it can capture wind energy, and the faster it grows. It's a self-reinforcing process, which is why waves can build to tremendous sizes during storms. But waves don't grow indefinitely. There are limits. The relationship between wind speed, the duration the wind blows, and the distance over which it blows, called the fetch, determines how large waves can become. These three factors, speed, duration, and fetch, are the fundamental ingredients in wave creation. A gentle breeze blowing for a few minutes across a small pond will create only small waves. But a powerful storm wind blowing for hours or days across hundreds of miles of open ocean can generate enormous waves, some reaching heights of over 30 meters, that's nearly 100 feet, as tall as a 10-story building. These monster waves, created by the most violent storms, are rare but very real, and they've been the doom of many ships throughout history. In 1933, a naval officer aboard the USS Ramapo reported observing a wave during a Pacific storm that he calculated, using careful triangulation from the ship's mast, to be approximately 112 feet high, about 34 meters. This observation was met with skepticism at the time, as such waves seemed impossibly large. But modern research has confirmed that waves of this size can indeed occur in severe storms. These aren't rogue waves or freak accidents of nature, they're simply the natural result of extreme wind conditions persisting over vast distances. What's fascinating is that once waves are generated, they don't immediately disappear when the wind stops blowing. Instead, they continue traveling across the ocean, sometimes for thousands of miles, carrying the energy imparted by that distant wind. These traveling waves are called swell, and they're different in character from the choppy, irregular waves you see in a local windy area. Swell waves are more organized, more regular. As waves travel away from the storm or windy area that created them, they sort themselves by wavelength, the distance from one wave crest to the next. Longer waves travel faster than shorter waves, so they gradually separate out, with the longest, fastest waves arriving at distant shores first, followed by progressively shorter waves. This is why experienced surfers and sailors can sometimes predict the approach of a distant storm by observing changes in the swell pattern. The waves themselves are messengers, carrying news of far-off weather. The speed at which waves travel is determined by their wavelength. In deep water, that is, water deeper than about half the wavelength, the relationship is beautifully simple. Longer waves travel faster. The speed of a deep water wave is approximately 1.25 times the square root of its wavelength in meters, when speed is measured in meters per second. A wave with a wavelength of 100 meters travels at about 12.5 meters per second, or roughly 28 miles per hour. A wave with a wavelength of 400 meters travels at about 25 meters per second, or 56 miles per hour. This means that the longest ocean swells can race across entire ocean basins in just a few days. Waves generated by a storm near Antarctica can travel northward across the Pacific and arrive at the beaches of California within a week, carrying energy across more than 6,000 miles of ocean. The water itself doesn't travel this distance. Individual water molecules mainly bob up and down and in small circles as waves pass. But the wave pattern, the organized motion, the energy, these travel onward, a ripple of information spreading across the sea. This realization, that waves carry energy without transporting water over long distances, was crucial to understanding ocean waves. When you watch a wave approaching shore, it might seem like the water itself is rushing toward the beach. But if you watch a piece of seaweed or a floating bottle as waves pass beneath it, you'll see it mainly bobs in place, moving slightly forward and back, up and down, but not traveling with the wave. The wave is a traveling pattern of energy and motion, not a mass transport of water. The mathematics of wave motion were worked out in the 18th and 19th centuries by physicists and mathematicians including Leonard Euler, Pierre-Simon Laplace, and George Airy. Their equations, still used today, describe how waves of different sizes behave, how fast they travel, how their shape changes. These equations revealed that ocean waves are fundamentally similar to other wave phenomena in nature: sound waves, light waves, seismic waves, all following mathematical principles that transcend the specific medium through which they travel. But ocean waves have unique characteristics too, shaped by the properties of water and the forces acting on it. Unlike sound waves traveling through air or light waves traveling through space, ocean waves exist at an interface, the boundary between water and air, and they're shaped by gravity pulling the water downward and momentum carrying it forward. This creates the characteristic rolling, rising and falling motion we associate with ocean waves, a motion that's both powerful and graceful, chaotic and ordered. And so waves are born from wind, shaped by physics, and sent traveling across thousands of miles of open ocean. Each wave carries a memory of the storm that created it, encoded in its size, its speed, its rhythm. And as these waves journey across the deep, they're heading toward an inevitable encounter with the shore, where their story takes a dramatic turn. But before we explore what happens when waves meet land, rest here for a moment in the deep ocean, where waves roll endlessly across blue water, where the motion is steady and eternal, where energy dances through liquid in patterns older than civilization itself. Take a slow, deep breath. Imagine yourself floating safely on this gentle swell, rising and falling, cradled by the ocean's rhythm, rocked by forces that have shaped Earth's shores for billions of years. The waves roll on. Patient. Timeless. Beautiful in their simple, eternal dance. In our next segment, we'll follow these waves toward shore and discover what happens when they finally encounter the land, how they transform, how they break, and how they've shaped the very edges of our continents. For now, let the rhythm of waves lull you into peace. The ocean breathes in and out, and so do you. All is well. All is calm. We've journeyed across the deep ocean, watching waves form from wind and travel thousands of miles as organized swell. Now, let's follow these waves as they approach the shore, where their character transforms and their long journey finally comes to an end. Let's continue our peaceful exploration together. Imagine a wave that began its life days ago in a storm near New Zealand. It's been traveling across the Pacific Ocean, moving through deep water where the ocean floor lies thousands of meters below. The wave has maintained its shape, rolling steadily northward, carrying energy across the vast expanse. But now, as it approaches the California coast, something begins to change. The ocean floor starts to rise. The wave is moving from deep water into what oceanographers call shallow water. In this transition, this meeting of wave and rising seafloor, transforms everything about how the wave behaves. In deep water, as we learned, a wave's speed depends only on its wavelength. But shallow water is defined differently than you might expect. A wave is considered to be in shallow water when the water depth is less than about 1/20th of the wavelength. For a wave with a wavelength of 200 meters, shallow water means anything less than about 10 meters deep. This might seem quite deep to us, but to the wave, it's shallow. When a wave enters shallow water, something remarkable happens. It begins to feel the bottom. The circular motion of water particles within the wave, those orbital paths we mentioned earlier, start to be disrupted by the presence of the seafloor below. The bottom of these circular orbits gets compressed, flattened, dragged against the ocean floor. This interaction with the bottom causes the wave to slow down. And here's where the physics becomes beautiful. As the wave slows, its wavelength decreases, the distance between crests gets shorter. But the period of the wave, the time between successive crests passing a fixed point, remains the same. The same amount of energy is still passing through, but now in a shorter horizontal distance. What happens to a wave when the same energy gets compressed into a shorter space? The wave grows taller. Its height increases. This is why waves that seem modest out at sea can build into impressive breakers as they approach shore. The shoaling effect, as it's called, concentrates the wave's energy vertically as it loses speed horizontally. As our Pacific wave continues toward shore, slowing and growing taller, another factor comes into play: refraction. This is the same phenomenon that makes a straw appear bent when you put it in a glass of water, but on a much grander scale. Wave refraction occurs because different parts of a wave often encounter shallow water at different times. Imagine a wave approaching a coastline at an angle. The part of the wave closer to shore enters shallow water first and begins to slow down, while the part still in deeper water continues at its original speed. This causes the wave to bend, to pivot, gradually turning to become more parallel to the shore. This bending of waves through refraction has profound effects on coastal geography. Waves tend to concentrate their energy on headlands, points of land that jut out into the sea, because the waves bend around these protrusions and approach from multiple angles, focusing energy on the exposed point. Conversely, bays receive less wave energy because the waves spread out as they bend into the curved shoreline. Over centuries and millennia, this differential wave energy helps explain why headlands erode more quickly while bays fill in with sediment, gradually smoothing out coastlines. Sailors and coastal dwellers have observed these patterns for thousands of years, but the mathematical understanding of wave refraction came in the early 20th century. In the 1940s, scientists developed techniques to draw refraction diagrams, maps showing how waves bend as they approach coasts of different shapes and depths. These diagrams became crucial tools for coastal engineering, helping predict where wave energy would be concentrated and where harbors might be safely built. But let's return to our wave, now approaching very close to shore. It has slowed, grown taller, and bent to align with the coastline. The water depth continues to decrease. And then, at a critical moment, something dramatic happens. The wave becomes unstable and breaks. Wave breaking is one of the most complex and beautiful phenomena in all of fluid dynamics. Despite centuries of study, the exact details of how and when waves break are still subjects of active research. But we understand the general principles. A wave becomes unstable when its height reaches a critical relationship to the water depth and wavelength. The most common rule of thumb is that waves break when the wave height becomes greater than about 78% of the water depth. At this point, the wave has simply become too tall and too steep to support itself. The crest of the wave is moving faster than the wave as a whole can travel, and the top literally outruns the bottom. What happens next depends on the shape of the seafloor and the characteristics of the wave. There are several types of breaking waves, each creating different patterns in the water. Spilling breakers occur on gently sloping beaches. These waves break gradually, with white water spilling down the front face of the wave as it moves toward shore. The breaking process starts well offshore and continues as the wave moves shoreward, dissipating energy slowly and continuously. These are the gentlest breakers, and beaches with spilling waves are typically the safest for swimming. Plunging breakers form on moderately steep beaches and are the classic tube or barrel waves beloved by surfers. These waves remain stable until they reach shallow water, then break suddenly and dramatically, with the crest curling over and plunging down into the trough ahead of the wave. The energy release is more concentrated than in spilling breakers, creating that iconic hollow space inside the breaking wave, the tube that surfers dream of riding through. Surging breakers occur on very steep beaches or near cliffs. These waves don't actually break in the conventional sense. Instead, they surge up the beach face, their energy absorbed by the steep slope. The wave face remains largely intact until it hits the shore, then rushes up and back down in a powerful surge. These waves can be dangerous because of their power and the strong backwash they create. The study of breaking waves gained scientific rigor in the 20th century, particularly through the work of researchers like Willard Bascom, who in the 1950s and 60s conducted extensive observations of waves at beaches around the world. Bascom documented how wave type, beach slope, and sand grain size all interact to shape coastal dynamics. His book Waves and Beaches, published in 1964, brought the science of waves to a general audience and remains a classic introduction to coastal oceanography. When a wave breaks, tremendous energy is released in a short time. The kinetic energy that the wave has carried across sometimes thousands of miles of ocean is finally dissipated, converted into sound, heat, turbulence, and the motion of water and sand. A single large breaking wave can release energy equivalent to several tons of TNT, though this energy is released more gradually than an explosion. This energy does work on the coastline. Breaking waves lift sand and carry it up the beach face. They erode rock, gradually wearing away even the hardest stone. They sort sediments by size, with larger particles settling in different zones than smaller ones. Over time, wave action sculpts the coast, creating the beaches, cliffs, sea stacks, and coastal caves that define the edge between land and sea. But waves don't simply crash on the beach and disappear. After breaking, the water must return to the sea, and this return flow creates its own patterns and hazards. The water that waves push up onto the beach flows back as backwash, and in certain conditions, this returning water can organize into narrow, powerful currents flowing seaward, rip currents. Rip currents form when the returning water finds a path of least resistance back through the surf zone, often through a break in a sandbar or a deeper channel. Water from a wide section of beach funnels into these narrow channels, creating currents that can flow seaward at speeds of up to 2 meters per second, faster than most people can swim. These currents are responsible for the majority of beach rescues performed by lifeguards each year. The danger of rip currents was not widely understood until the mid-20th century. Shepard Phelps, an Australian lifeguard, was among the first to systematically study and name these currents in the 1930s. He recognized that what had been called various names, undertow, runouts, or rips, were actually a specific type of current with predictable behavior. His work, and that of coastal scientists who followed, helped develop safety protocols that have saved countless lives. The key to surviving a rip current is understanding that it's a surface current flowing away from shore, not a pulling force dragging you under. The current is typically narrow, so swimming parallel to shore, perpendicular to the current, will carry you out of it. Then you can swim back to shore outside the rip current's path. Fighting against the current by swimming directly toward shore exhausts even strong swimmers, which is why rip currents are so dangerous despite rarely being more than a few dozen meters wide. And so our wave, born days ago in a distant storm, traveling thousands of miles across the Pacific, has finally completed its journey. It shoaled and slowed, refracted and bent, grew tall and unstable, then broke in a cascade of white water and energy. The water returns to the sea, perhaps to be lifted again by the next wave, continuing the eternal cycle. Think about the energy that wave carried: wind energy transferred to water, transported across an ocean, and finally released here at the shore in a moment of turbulence and sound. Every wave that breaks on every beach is completing a similar journey, each one a story of energy transformation and travel. Take a slow, deep breath. Listen, if you can imagine it, to the sound of waves breaking rhythmically on a shore. That sound has been the Earth's heartbeat for billions of years, long before there were ears to hear it. Constant, soothing, eternal. The waves come in, one after another, and each one is unique, yet each one is part of the same timeless pattern. In our next segment, we'll explore the intricate dance between waves and beaches, how waves build beaches up and tear them down, how they create the patterns of sand we see, and how coastal communities have learned, sometimes painfully, to live with the power of the sea. For now, rest in the rhythm. The waves break, the water returns, and the cycle continues. All is as it should be. All is peace. We've followed waves from their birth in distant storms to their dramatic finale at the shore. Now, let's explore the intimate relationship between waves and the beaches they sculpt, the patterns they create, and the delicate balance between destruction and creation that shapes our coasts. Let's continue this peaceful journey together. Stand on any beach and look down at the sand beneath your feet. That sand has a story to tell, a story written by waves over days, years, and millennia. The beach you see today is not a permanent feature of the landscape, but rather a temporary arrangement of sediment, constantly being rearranged by the waves that caress and pound the shore. Beaches are, in essence, rivers of sand flowing along the coast, driven by wave energy. This movement of sediment parallel to the shoreline is called longshore drift, or littoral drift, and it's one of the most important processes shaping coastlines around the world. Here's how it works. When waves approach the shore at an angle, which they almost always do, they push water and sand up the beach face at that same angle. But when the water returns to the sea as backwash, gravity pulls it straight down the slope, perpendicular to the shoreline. The result is a zigzag pattern of movement. Sand grains move up the beach at an angle, then back down perpendicular to shore, then up at an angle again with the next wave, then back down. Step by step, wave by wave, sand migrates along the coast. In some locations, longshore drift can transport hundreds of thousands of cubic meters of sand per year. Along the coast of Southern California, for example, sand moves predominantly from north to south, driven by the prevailing wave direction. Over a human lifetime, this transport can carry sand grains dozens or even hundreds of kilometers from where they originally entered the ocean from rivers or eroding cliffs. This discovery of longshore drift's importance came gradually through the 19th and 20th centuries, but one event made it dramatically clear to coastal engineers. In the early 20th century, harbors and ports began building jetties and groins, structures extending perpendicular to the shore designed to protect harbor entrances or trap sand to widen beaches. What happened next surprised many people. Sand accumulated dramatically on one side of these structures while the beach on the other side eroded away. At Santa Barbara, California, a breakwater built in 1928 to protect the harbor entrance created a massive problem. Sand moving southward along the coast began piling up north of the breakwater, while beaches south of the harbor, starved of their normal sand supply, began to disappear. Within a few years, the harbor itself began filling with sand that could no longer bypass the breakwater. Engineers had to install a permanent sand bypassing system, using dredges to pump sand from the harbor to beaches south of the breakwater, essentially doing mechanically what the waves had done naturally before the breakwater was built. This pattern repeated at coastal structures around the world, teaching engineers a crucial lesson: you cannot interrupt the natural flow of sand along a coast without consequences both updrift and downdrift from your structure. The coast is an interconnected system, and what happens at one location affects beaches for miles in either direction. But longshore drift is just one way waves move sand. Waves also move sediment perpendicular to the shore, onshore and offshore, in patterns that change with the seasons and the character of the waves. During winter in many locations, powerful storm waves with short periods between crests tend to erode beaches, carrying sand offshore and depositing it in sandbars beneath the surf zone. These storm waves break with great force, stirring up sand and carrying it seaward in the undertow and rip currents. The beach profile becomes steeper and narrower, and beachgoers might notice that the beach has disappeared during winter months. Then, during summer, gentler waves with longer periods between crests gradually push that sand back on shore. These constructive waves, as they're called, build the beach back up, creating the wide, gentle beaches perfect for summer recreation. The sand that seemed lost during winter was simply resting offshore, waiting for calmer conditions to return it to the beach. This seasonal cycle of beach erosion and accretion was first carefully documented by Francis Shepard, a pioneering marine geologist who, in the 1930s and 40s, conducted detailed surveys of beach profiles at Scripps Beach in La Jolla, California. Shepard measured the beach profile repeatedly over many years, creating a detailed record of how the beach changed shape seasonally and in response to individual storms. His work revealed that beaches are dynamic systems in constant flux, responding sensitively to changes in wave conditions. The size and character of sand grains themselves also tell a story about wave energy. On high-energy beaches pounded by powerful waves, the sand tends to be coarser, made of larger particles. This happens because strong waves can keep fine sand suspended in the water, carrying it away, while larger, heavier grains settle and remain on the beach. On low-energy beaches protected from large waves, the sand can be much finer, sometimes almost like powder. Some beaches aren't made of sand at all, but of pebbles or cobbles, smooth, rounded stones ranging from marble-sized to fist-sized or larger. These shingle beaches, as they're called, are common in areas where wave energy is very high and where the source material is rocky rather than sandy. The waves gradually round the stones, tumbling them in the surf until all the sharp edges are worn away. Walking on a shingle beach, you hear a distinctive sound, the musical rattle and clatter of stones being pulled by the backwash, a sound that has inspired poets and painters for centuries. The shape of waves also creates distinctive patterns in beach sand that you can observe on any shore. Ripple marks, small, regular ridges in the sand running parallel to shore, are created by the orbital motion of water and waves. These ripples typically have wavelengths of just a few centimeters and heights of a centimeter or less, but they cover vast areas of the seafloor in shallow water. The spacing and orientation of ripple marks tell geologists about the waves that created them, and ancient ripple marks preserved in sedimentary rocks tell us about wave conditions in long-vanished seas. Near the water's edge, you might notice another pattern, cusps. Beach cusps are rhythmic, crescent-shaped features in the beach face, with horns of coarser material pointing seaward and embayments of finer sand between them. They typically occur in regular series, with spacing that can range from a few meters to tens of meters. The exact mechanism that creates beach cusps has been debated for over a century, but they appear to form through a kind of self-organizing feedback between wave action and beach topography. Once a small irregularity forms, it tends to grow and become more pronounced as waves preferentially erode some areas while depositing in others. The study of beach cusps became particularly intense in the 1950s and 60s, with researchers proposing various theories about their formation. Some suggested they were created by edge waves, standing waves that travel along the shore rather than toward it. Others proposed that they result from two wave trains intersecting at an angle. The debate continues, but most researchers now believe that multiple mechanisms can create cusps, depending on local conditions. Beyond the visible beach lies the surf zone, that area of churning white water where waves break and reform, sometimes breaking multiple times before finally rushing up the beach face. The surf zone is one of the most energetic and complex environments in the ocean, a place where turbulence reigns and where tremendous amounts of energy are dissipated. Within the surf zone, sandbars often form parallel to shore. These underwater ridges of sand are built by breaking waves, which stir up sediment and deposit it in characteristic patterns. The number, size, and position of sandbars vary depending on wave conditions, beach slope, and sediment characteristics. Some beaches have a single nearshore bar, while others have multiple bars extending hundreds of meters offshore. These sandbars play a crucial role in protecting the beach from erosion. When waves break on an offshore sandbar, they dissipate much of their energy there rather than at the beach face itself. During major storms, sandbars can absorb tremendous amounts of wave energy, helping to protect coastal development. After the storm passes, The gentle post-storm waves gradually move sand from the bars back toward the beach, repairing the damage. The recognition of sandbars' protective function has influenced modern coastal management strategies. Rather than building hard structures like seawalls, which can actually worsen erosion by reflecting wave energy, some coastal communities now focus on maintaining healthy beach and sandbar systems through beach nourishment, adding sand to beaches to replace what's been lost to erosion and sea level rise. This approach became widespread in the latter half of the 20th century, particularly in the United States and Europe. The U.S. Army Corps of Engineers has conducted hundreds of beach nourishment projects, pumping millions of cubic meters of sand onto eroding beaches. The sand typically comes from offshore deposits or from dredging projects at harbor entrances. While expensive and requiring periodic renourishment, this approach works with natural coastal processes rather than against them. So the beach beneath your feet is not solid, not permanent, but flowing, a river of sand moving along the coast, shifting onshore and offshore with the seasons, sorted by wave energy into patterns and textures. Every grain has traveled, perhaps for decades or centuries, tumbled by waves, carried by currents, part of a vast system of sediment exchange that has been operating since long before humans walked these shores. Think about that for a moment. The sand you might have walked on during a summer vacation, the sand that felt so solid and dependable beneath your feet, was actually in motion, part of a slow dance choreographed by waves, constantly arriving from somewhere up coast and departing towards somewhere down coast. Take a slow, deep breath. Imagine the gentle sound of sand grains settling, the whisper of millions of tiny particles finding their temporary resting places before the next wave moves them again. The beach breathes with the ocean, swelling and shrinking, moving and changing, yet somehow remaining recognizable, familiar, eternal in its impermanence. In our next segment, we'll explore some of the more dramatic and dangerous aspects of ocean waves, from tsunamis to rogue waves, from storm surges to the waves that reshaped coastlines and changed human history. For now, rest in the knowledge that even in constant change, there is pattern. Even in motion, there is rhythm. The beach flows like a river, yet the waves still break in their timeless pattern, one after another, endlessly. All is well. All is calm. The ocean knows what it's doing. We've explored how waves sculpt beaches and move sand in endless patterns along our coasts. Now, let's turn our attention to some of nature's most powerful and extraordinary waves, the giants that have shaped human history and continue to remind us of the ocean's awesome power. Let's continue our peaceful journey, even as we explore these mighty forces. Most of the waves we've discussed so far are what oceanographers call wind waves, generated by wind blowing across the ocean surface. But there are other types of waves, created by different forces, and some of these are among the most powerful phenomena on Earth. Let's begin with tsunamis, waves that have nothing to do with wind, yet can travel across entire ocean basins and devastate coastlines thousands of kilometers from where they originate. The word tsunami comes from Japanese, tsu meaning harbor and nami meaning wave, because these waves often go unnoticed in the open ocean but become devastatingly obvious when they enter harbors and coastal areas. Tsunamis are sometimes incorrectly called tidal waves, but they have nothing to do with tides. They're generated by sudden vertical movements of the seafloor, most commonly during undersea earthquakes, but also by submarine landslides, volcanic eruptions, or even meteorite impacts. When an earthquake occurs beneath the ocean, and the seafloor suddenly shifts vertically, dropping or rising by several meters, it displaces an enormous volume of water. This displacement creates waves that radiate outward from the source in all directions, like ripples spreading from a stone dropped in a pond, but on a vastly larger scale. What makes tsunamis so different from wind waves is their wavelength. While wind waves typically have wavelengths of 100 meters or so, tsunamis can have wavelengths of 100 to 200 kilometers. That's the distance from crest to crest. This enormous wavelength means that tsunamis behave as shallow water waves even in the deepest parts of the ocean, because remember, a wave is in shallow water when the depth is less than 1/20th of its wavelength. In the deep ocean, a tsunami might be only a meter high, barely noticeable, but it travels at tremendous speed. The speed of a shallow water wave is determined by the water depth, following the formula that speed equals the square root of gravity times depth. In the deep Pacific, where depths average about 4,000 meters, tsunamis travel at roughly 700 kilometers per hour, about the speed of a jet aircraft. At this speed, a tsunami can cross the Pacific Ocean in less than a day. The 2004 Indian Ocean tsunami, triggered by a magnitude 9.1 earthquake off the coast of Sumatra, demonstrated the devastating power of these waves with tragic clarity. The earthquake, one of the largest ever recorded, ruptured a fault zone over 1,200 kilometers long, displacing the seafloor by several meters and generating tsunamis that radiated across the Indian Ocean. In the deep ocean, ships didn't even notice the waves passing beneath them. But when those waves reached coastlines, in Indonesia, Thailand, Sri Lanka, India, and even as far away as the coast of Africa, they had transformed into walls of water up to 30 meters high in some locations. The tsunami struck without warning in many places because the Indian Ocean, unlike the Pacific, had no tsunami warning system in place at the time. The waves killed more than 230,000 people across 14 countries, making it one of the deadliest natural disasters in recorded history. In the aftermath, the international community worked rapidly to establish tsunami warning systems in the Indian Ocean and to improve systems worldwide. Modern tsunami warning centers use networks of seismometers to detect earthquakes that might generate tsunamis, and arrays of ocean buoys equipped with seafloor pressure sensors that can detect the passage of tsunami waves in the open ocean. When a potential tsunami is detected, warnings can be issued to coastal areas in the wave's path, providing precious time for evacuation. These systems have saved countless lives in subsequent events, though the challenge of providing timely warnings for nearby coasts, where tsunamis arrive within minutes of the triggering earthquake, remains difficult. One of the most fascinating aspects of tsunamis is how they behave when they approach shore. As the wave enters shallow water, it slows dramatically, from jet aircraft speed in the deep ocean to perhaps 50 kilometers per hour in coastal waters. And remember what happens when waves slow down: the wavelength decreases and the height increases. A tsunami that was barely noticeable in deep water can grow to tremendous height as it approaches shore, with the wave energy that was spread over hundreds of kilometers of wavelength now compressed into a much shorter distance. Tsunamis often don't appear as a single breaking wave, but rather as a rapid rise in sea level, a flooding that continues for several minutes as the wave's enormous wavelength pushes water onto land. Then the water withdraws, sometimes exposing the seafloor far from the normal shoreline, before the next wave arrives. Tsunami events typically include multiple waves, sometimes continuing for hours, and later waves can be larger than the first, which is why evacuation must continue until authorities declare the danger has passed. While tsunamis are among the most powerful waves, they're relatively rare. More common, yet still extraordinary, are storm surges, the rise in sea level that occurs during major storms, particularly tropical cyclones like hurricanes and typhoons. Storm surge is not a wave in the traditional sense, but rather a dome of elevated water pushed ahead of and around a storm system. It's created by a combination of factors: the low atmospheric pressure at the storm center, which allows the ocean surface to rise, and more significantly, the powerful winds that push water toward shore. When this elevated water reaches the coast, it can raise sea level by several meters above the normal tide level, flooding coastal areas. The most deadly storm surge in recent U.S. history occurred during Hurricane Katrina in 2005, when surge heights of up to 8.5 meters devastated the Mississippi coast and contributed to the catastrophic flooding of New Orleans. But the deadliest storm surge ever recorded occurred in 1970, when the Bola cyclone struck the coast of East Pakistan, now Bangladesh. The storm surge, estimated at up to 10 meters high, swept over the low-lying Ganges Delta Islands, killing between 300,000 and 500,000 people. The exact number may never be known. Bangladesh, with its vast low-lying coastal areas and dense population, remains particularly vulnerable to storm surge. The nation has invested heavily in coastal shelters and early warning systems, and these preparations have significantly reduced death tolls in subsequent cyclones. The 1970 disaster, however, remains a stark reminder of the ocean's power and the vulnerability of coastal populations. Storm surge is made worse when it coincides with high tide, what's called the astronomical tide. The combination of storm surge and high tide is known as storm tide, and it determines the total water level that impacts the coast. This is why the timing of a hurricane's landfall matters so much. A storm making landfall at high tide will cause far more coastal flooding than the same storm arriving at low tide. Now, let's turn to a different type of extraordinary wave, one that sailors whispered about for centuries but that scientists long dismissed as mere legend: the rogue wave. Rogue waves, also called freak waves or monster waves, are unexpectedly large waves that appear seemingly out of nowhere in the open ocean. They're defined as waves at least twice the height of the surrounding waves, so in seas where typical waves are 6 meters high, a rogue wave would be 12 meters or more. These waves are steep, often described as having a wall of water appearance, and they can pose serious danger even to large ships. For centuries, sailors reported encounters with these abnormal waves, describing walls of water that appeared suddenly and without warning, sometimes in otherwise moderate seas. But scientists were skeptical. The statistical models used to predict wave heights suggested that such extreme waves should be vanishingly rare, so rare that they should hardly ever occur. The reports were dismissed as exaggerations, or attributed to ships encountering unusual conditions like waves interacting with strong currents. Then, on January 1, 1995, something happened that changed the scientific understanding of rogue waves forever. At the Dropner oil platform in the North Sea, a laser measurement device recorded a wave with a height of 25.6 meters, 84 feet, and seas where the significant wave height was only about 11 meters. This was the first scientific measurement of a rogue wave, and it proved that these giants were real, not legendary. The Dropner wave measurement sparked intense research into rogue wave formation. Scientists discovered that these waves are more common than statistical models had predicted. Analysis of radar data from ocean buoys and satellites has revealed that several rogue waves occur somewhere in the world's oceans every day. They are rare at any given location, but in the vastness of the global ocean, they're constantly occurring somewhere. Several mechanisms can create rogue waves. One is constructive interference. When multiple waves traveling in slightly different directions meet and their crests align, they can combine to create a much larger wave. Another mechanism involves wave focusing through refraction, particularly where waves interact with strong ocean currents like the Agulhas Current off South Africa, which is notorious for generating rogue waves. A third mechanism, discovered more recently, involves a phenomenon from physics called modulation instability, where energy can spontaneously concentrate into a single large wave under certain conditions. The recognition that rogue waves are real and relatively common has led to changes in ship design standards and weather routing services that help ships avoid areas where rogue waves are more likely. It's also led to a deeper appreciation that the ocean's surface is more complex and less predictable than simple statistical models suggest. So the ocean holds many types of waves, from the gentle swells we've been discussing to these extraordinary phenomena: tsunamis racing across ocean basins at jet speed, storm surges raising sea levels by meters, rogue waves rearing up without warning in the open sea. Each type follows the laws of physics, yet each reminds us that nature can be both beautiful and formidable. Take a slow, deep breath. Even in discussing these powerful forces, we can find a kind of peace in understanding them, in knowing that humans have learned to predict, to warn, to prepare. Knowledge transforms fear into respect, and respect allows us to live wisely alongside the ocean's power. The sea is mighty, yes, but we are learning its language, reading its signs, and finding ways to coexist with its tremendous forces. In our next segment, we'll explore some of the more subtle and fascinating aspects of ocean waves, internal waves hidden beneath the surface, the intricate connection between waves and tides, and the ways waves transport energy and shape our planet's climate. For now, rest in the rhythm. Even the mightiest tsunami follows the same physical laws as the gentlest ripple. All waves are part of the same family, expressions of energy moving through water, each telling its own story in the eternal language of the sea. All is well. The ocean's power is balanced by its predictability. We are safe here, learning and wondering together. We've explored the ocean's most dramatic waves, tsunamis, storm surges, and rogue waves. Now, let's discover some of the ocean's hidden secrets, waves you cannot see from the surface, the intricate dance between waves and tides, and the profound ways that waves shape our planet's climate and ecosystems. Let's continue our peaceful exploration together. When we think of ocean waves, we naturally picture the surface, the visible interface between water and air where waves rise and fall in their endless rhythm. But beneath the surface, hidden from view, another world of waves exists, sometimes far larger than anything visible at the ocean's surface. These are called internal waves, and they travel not at the boundary between water and air, but at boundaries between layers of water with different densities. The ocean is not uniform, it's stratified into layers. Warmer, less salty water tends to float above colder, saltier, denser water. The boundary between these layers, called the thermocline or pycnocline, can support waves much as the ocean surface does. Internal waves can be enormous. While surface waves rarely exceed 30 meters in height except in the most extreme conditions, internal waves can be hundreds of meters tall, taller than skyscrapers, yet remain completely invisible from the surface. A submarine traveling at the thermocline depth might experience significant vertical motion from internal waves, while a ship sailing above would notice nothing unusual. These hidden giants were first discovered during World War I, when submarines found themselves mysteriously pushed upward or downward by invisible forces. Submariners reported being unable to maintain depth, their vessels rising or falling despite their efforts to remain at constant depth. It wasn't until later that scientists realized these submarines were encountering internal waves at the thermocline. The study of internal waves accelerated during the Cold War, when submarine detection became a military priority. Researchers discovered that internal waves are generated by many processes: tidal currents flowing over underwater ridges and continental slopes, wind forcing at the surface that creates oscillations at the thermocline, and the interaction of currents with seafloor topography. Like surface waves, internal waves can travel vast distances, carrying energy through the ocean's interior. One of the most spectacular displays of internal waves occurs in the Strait of Gibraltar, where Atlantic water flowing into the Mediterranean over the shallow sill creates powerful internal waves that propagate into the Mediterranean basin. These waves can be seen from space in satellite images as alternating bands of rough and smooth surface water, even though the waves themselves are traveling hundreds of meters below the surface. The surface expression occurs because internal waves create convergent and divergent currents at the surface, which smooth or roughen the surface water, making the internal wave pattern visible to radar. Internal waves play crucial roles in ocean ecology and climate. They bring nutrient-rich deep water upward toward the sunlit surface layers where photosynthesis occurs, fertilizing the ocean and supporting marine food webs. They also contribute to ocean mixing, stirring the stratified ocean and helping to distribute heat, salt, and other properties vertically through the water column. Understanding internal waves has become increasingly important for climate modeling, as they affect how heat is stored and transported in the ocean. Now, let's turn our attention to the relationship between waves and tides, a connection that might not be immediately obvious, but which profoundly affects coastal wave conditions. Tides, of course, are not waves in the same sense as wind waves. They're caused by the gravitational pull of the moon and sun on Earth's oceans, creating a rise and fall of sea level that typically occurs twice daily in most locations. But tides interact with waves in fascinating ways. The most obvious interaction is that tides change the water depth at the coast, and as we've learned, water depth affects how waves behave. At high tide, waves break farther up the beach, potentially reaching areas that are dry at low tide. The depth over sandbars and reefs changes with the tide, affecting where and how waves break. Surfers know this well. Many surf breaks only work properly at certain tidal stages when the water depth over the reef or sandbar is just right. But there's a more subtle interaction as well. Tidal currents, the horizontal movement of water associated with the rising and falling tide, can significantly modify waves. When waves travel with a tidal current, they lengthen slightly and decrease in height. When waves travel against a tidal current, they shorten and steepen, sometimes becoming much more dangerous. This interaction between waves and opposing currents is particularly significant at harbor entrances and tidal inlets, where strong currents flow as the tide floods in and ebbs out. Waves encountering an ebbing current, water flowing out of a harbor or inlet against incoming waves, can become dangerously steep and confused, creating hazardous conditions for boats. Many harbor entrances display warning signs about not crossing the bar during ebb tide and heavy seas, because this combination can create conditions that have capsized even experienced mariners. The Columbia River Bar, where the Columbia River meets the Pacific Ocean on the border between Oregon and Washington, is known as the graveyard of the Pacific because of these dangerous conditions. When large ocean swells encounter the strong outgoing current of the Columbia River, especially during spring tides when currents are strongest, waves can build to tremendous heights and break unpredictably. Since 1792, approximately 2,000 vessels and 700 lives have been lost at the Columbia River Bar, making it one of the most dangerous maritime navigation points in the world. Modern navigation has made the bar safer, with careful timing of crossings, powerful tugboats to assist vessels, and Coast Guard stations specifically devoted to bar rescues. But the fundamental physics, waves encountering opposing currents, still creates challenging conditions that command respect and caution. Beyond their interaction with tides, waves play a crucial role in the Earth's climate system, one that's often underappreciated. Waves are constantly mixing the upper ocean, stirring surface waters and helping to distribute heat. This mixing affects how much heat the ocean absorbs from the atmosphere and how quickly that heat spreads throughout the ocean. The ocean is the Earth's great thermal reservoir, storing far more heat than the atmosphere. The way waves mix the ocean's surface layer affects global climate patterns, the rate of climate change, and the behavior of phenomena like El Niño. Climate models must account for wave-driven mixing to accurately predict future climate, though the exact effects are still being researched. Waves also affect the exchange of gases between ocean and atmosphere. The turbulence created by breaking waves increases the surface area of contact between air and water, and it disrupts the thin layer of still water at the very surface, allowing gases to transfer more efficiently. This affects how much carbon dioxide the ocean absorbs from the atmosphere, a crucial process in the global carbon cycle. Without wave action, the ocean would absorb CO2 much more slowly, and atmospheric CO2 levels would be quite different. When waves break, they also inject air into the water, creating bubbles. These bubbles don't just disappear immediately, they can remain suspended in the water for significant periods, creating what's called the bubble layer beneath the ocean surface. This bubble layer affects how sound travels through the ocean, which has implications for marine mammals that use sound for communication and navigation, and for human technologies like sonar. The sound of breaking waves themselves is one of the ocean's most characteristic features. That soothing, rushing sound of waves on a beach is actually created by the popping of countless tiny bubbles as air is released from the turbulent water. Each bubble, as it bursts, creates a tiny sound, and the combination of billions of bubbles creates the continuous sound we associate with the surf. This sound varies with wave size and type. The gentle whisper of small waves lapping on sand sounds completely different from the thunderous roar of large waves crashing on rocks. Scientists have studied wave sounds not just for their own sake, but because they provide information about wave conditions. During World War II, researchers discovered they could estimate wave heights in distant storms by analyzing the low-frequency sound those waves created, sound that travels through the ocean for hundreds of kilometers. This technique, called ocean acoustics, is still used today to monitor ocean conditions in remote areas where direct measurements are difficult. Waves also create sounds in another, less obvious way. Large waves traveling across the deep ocean create pressure fluctuations on the seafloor, and in some frequency ranges, this creates seismic waves, vibrations that travel through the solid earth. Seismologists can detect these ocean-generated seismic signals, called microseisms, on seismometers anywhere on Earth. During large storms, the microseism signal increases dramatically as huge waves pound the ocean in the storm area. For many years, microseisms were considered noise, unwanted signals that interfered with detecting earthquakes. But researchers have learned to use microseisms as a tool for monitoring ocean wave conditions globally. By analyzing seismic data from networks of seismometers around the world, scientists can track the size and location of major storms at sea, even in areas where there are no wave buoys or weather stations. This reveals something profound. Waves connect the ocean not just to the atmosphere above, but to the solid earth below. Energy flows between air, water, and rock, all mediated by the motion of waves. The earth is not a collection of separate systems but an integrated whole, and waves are one of the threads that weave these systems together. So beneath the visible waves at the surface, there are hidden waves hundreds of meters tall, traveling along invisible boundaries inside the ocean. Waves interact with tides and currents in intricate ways that can turn placid waters dangerous. They mix the ocean and affect global climate. They create sounds that travel through water and rock. They connect systems in ways we're still discovering. Take a slow, deep breath. The ocean is more complex, more interconnected, more alive with motion than we can see from the shore. Every wave at the surface is connected to processes above, below, and within, part of a grand system of energy and motion that encompasses the entire planet. Think of it, the same waves that lull us to sleep with their rhythmic sound are affecting climate, nourishing ecosystems, creating seismic signals in the Earth's crust. Everything is connected. Everything flows together in patterns we're only beginning to fully understand. In our next segment, we'll explore how humans have learned to harness wave energy, how waves have inspired art and culture throughout history, and how our relationship with waves continues to evolve in an era of rising seas and changing climate. For now, rest in the knowledge that you are part of this interconnected system. The oxygen you breathe was partially regulated by wave action transferring gases between ocean and atmosphere. The climate you experience has been shaped by waves mixing the ocean. You are connected to the waves, as all life on Earth is connected to the sea. All is well. All is connected. All is part of the endless rhythm. We've explored the hidden depths of internal waves and the intricate connections between waves, tides, and climate. Now, let's discover how humanity has learned to live with waves, harness their power, and find inspiration in their eternal rhythm. Let's continue this peaceful journey together. For as long as humans have lived near the ocean, we have been drawn to waves, mesmerized by their power, soothed by their rhythm, challenged by their unpredictability. waves have shaped human culture, inspired art and music, and influenced where and how coastal communities develop. And in recent decades, we've begun to harness wave energy itself, turning the ocean's motion into electricity. The idea of extracting energy from waves is not new. In 1799, a French engineer named Pierre-Simon Girard filed what may be the first patent for a wave energy device, though his invention was never built. Throughout the 19th and early 20th centuries, various inventors proposed wave energy machines, but none achieved commercial success. The challenge was, and remains, how to efficiently convert the irregular, multidirectional motion of waves into useful energy. Interest in wave energy surged during the 1970s oil crisis, when the world suddenly became acutely aware of its dependence on fossil fuels. Researchers, particularly in the United Kingdom, began serious scientific investigation of wave power. One pioneer was Stephen Salter of the University of Edinburgh, who in 1974 developed what became known as Salter's duck, a floating device shaped to bob with waves in a way that could theoretically convert up to 90% of wave energy into electricity. Salter's duck was never commercialized at large scale, but it demonstrated that wave energy conversion was theoretically possible with high efficiency. Since then, dozens of different wave energy technologies have been developed and tested. Some use floating buoys that move up and down with waves, driving hydraulic pumps or linear generators. Others use oscillating water columns, enclosed chambers where waves cause the water level to rise and fall, pushing air through a turbine. Still others use attenuator devices that flex like giant segmented snakes as waves pass along their length. The theoretical energy available from waves is enormous. The World Energy Council estimates that wave energy could potentially provide up to 2,000 terawatt-hours of electricity annually, roughly 10% of global electricity consumption. Coastal nations with high wave energy resources, particularly those facing the prevailing westerlies in the Atlantic and Pacific Oceans, have especially strong potential. The coasts of Scotland, Ireland, the Pacific Northwest of North America, Chile, South Africa, Australia, and New Zealand all receive powerful, consistent swells that contain tremendous energy. However, practical challenges have slowed wave energy development. The ocean is a harsh environment, salt water corrodes, storms damage equipment, and marine growth fouls surfaces. Wave energy devices must be robust enough to survive the worst storms yet efficient enough to capture energy from gentle swells. They must be maintained in difficult offshore conditions, and the electricity they generate must be transmitted to shore through underwater cables. These challenges have proven more difficult than early optimists anticipated. Despite these obstacles, progress continues. As of the early 2020s, several wave energy farms are operating or under development around the world. Portugal's Agricultura wave farm became the world's first commercial wave energy installation in 2008, though it operated for only a few months before being shut down for financial reasons. More recently, smaller pilot projects in Scotland, Australia, and the United States have demonstrated that wave energy can work, even if it's not yet cost competitive with other renewable energy sources like wind and solar. The promise remains compelling. Unlike solar panels that only work during daylight or wind turbines that depend on variable breezes, waves are remarkably consistent and predictable. Ocean swells arrive at coastlines day and night, through all seasons, providing a steady, reliable source of renewable energy. As technology improves and costs decrease, wave energy may yet fulfill its potential as a significant contributor to the world's clean energy future. Beyond generating electricity, waves have powered human activities in other ways throughout history. Traditional fishing communities around the world learned to read wave patterns to navigate safely and find productive fishing grounds. Polynesian navigators crossed thousands of miles of open Pacific Ocean without instruments, using their knowledge of swell patterns, along with stars, winds, and bird behavior, to find distant islands. These Polynesian wayfinding techniques, nearly lost in the 20th century, have been revived in recent decades through efforts like the Polynesian Voyaging Society. Navigators train for years to recognize subtle differences in swell direction and character, learning to detect how swells refract around islands that are still beyond the horizon. They can sense the presence of land they cannot see by changes in the wave field, a navigational feat that modern GPS users find almost incredible, yet one that allowed ancient Polynesians to settle islands across the vast Pacific. In the realm of sport and recreation, wave riding has ancient roots but has evolved into the global phenomenon of modern surfing. The earliest known accounts of wave riding come from Polynesia, where surfing was deeply integrated into Hawaiian culture long before European contact. When British explorer James Cook arrived in Hawaii in 1778, his crew observed Hawaiians riding waves on wooden boards, a practice that amazed them. Surfing nearly died out in Hawaii during the 19th century under pressure from missionaries who viewed it as idle and inappropriate. But in the early 20th century, it experienced a revival, championed by figures like Duke Kahanamoku, an Olympic swimming champion who traveled the world demonstrating surfing and sharing Hawaiian wave riding culture. Duke's efforts helped transform surfing from a nearly extinct Hawaiian tradition into an international sport and lifestyle. Modern surfing has driven much of the practical understanding of how waves break. Surfers are, in a sense, applied wave physicists. They must understand wave refraction, shoaling, the effects of wind and tide, the relationship between swell period and wave shape. The best surf spots in the world exist where particular combinations of seafloor bathymetry, swell exposure, and coastal geography create waves that break in just the right way. One of the world's most famous waves, Pipeline on the north shore of Oahu, Hawaii, breaks over a shallow reef in a way that creates a perfect, hollow barrel. The wave has been studied scientifically to understand exactly why it has such ideal shape. Researchers found that a unique combination of factors, the angle of the incoming swell, the shape and depth of the reef, and the steepness of the seafloor gradient, all converge to create Pipeline's distinctive form. Similar detailed studies have been conducted at other famous surf breaks, revealing how subtle changes in seafloor topography can dramatically affect wave shape. This scientific understanding of surf breaks has even led to the creation of artificial surfing reefs and wave pools. Engineers have designed and built underwater structures that modify natural wave patterns to improve surfing conditions. The world's first purpose-built artificial surfing reef was constructed at Cable Station in Western Australia in 1999, though it was removed in 2013 after failing to consistently produce quality waves. More successful have been inland wave pools, using various technologies to generate surfable waves in landlocked locations, bringing the ocean's waves to places hundreds of miles from the nearest coast. waves have also profoundly influenced art, literature, and music throughout human history. The Japanese artist Hokusai's The Great Wave off Kanagawa, created around 1830, has become perhaps the most recognizable image of a wave in art history. The print shows a towering wave dwarfing Mount Fuji in the background, with 3 boats caught in the wave's curl. Art historians note that Hokusai may have been depicting a particularly large wave, or perhaps exaggerating for dramatic effect, but the image captures something essential about waves: their beauty, their power, and their ability to make even permanent things like mountains seem small. In literature, waves serve as metaphors for time, change, impermanence, and the vast forces beyond human control. Virginia Woolf's novel The Waves, published in 1931, uses wave imagery throughout to explore consciousness and the passage of time. In Moby Dick, Herman Melville describes ocean waves with the precision of someone who truly understood the sea, drawing on his own experience as a sailor. The rhythm of waves has influenced poetry across cultures, with the meter and cadence of verse sometimes echoing the rise and fall of surf on shore. Musicians, too, have drawn inspiration from waves. The sound of the ocean has been incorporated into compositions throughout history, from Debussy's La Mer to contemporary ambient music designed to aid relaxation and sleep, much like the video you might be watching now. The repetitive yet varied nature of waves, never exactly the same, yet always following the same pattern, creates a sonic texture that humans find deeply soothing, perhaps because it connects us to something ancient and elemental. This soothing quality of wave sounds has been studied scientifically. Researchers have found that the rhythmic sound of waves can help induce relaxation and sleep by providing a form of white noise that masks other sounds, and by creating a predictable auditory pattern that the brain finds calming. The frequency spectrum of wave sounds, the particular mixture of low and high frequencies, appears to be especially conducive to relaxation, which may explain why recordings of ocean waves are among the most popular natural sounds used in meditation, sleep aids, and stress reduction programs. So waves have given us more than just a beautiful sight or a force to study. They've powered our imaginations, inspired our art, challenged our ingenuity, and offered us pathways to peace and renewal. From ancient Polynesian navigators reading swells to modern engineers harnessing wave power, from Hokusai's brushstrokes to the rhythm of this very narration, waves have woven themselves into the fabric of human culture. Take a slow, deep breath. Listen, if you can imagine it, to that timeless sound, the rush and whisper of waves breaking on shore. That sound has been humanity's lullaby since the first humans walked coastal shores. It's accompanied countless generations to sleep, soothed countless troubled minds, reminded countless souls of something larger than themselves. You are part of this long lineage, humans who have found comfort, inspiration, and wonder in the eternal rhythm of the sea. In our final segment, we'll bring our journey to a gentle close, exploring what waves mean for our future in an era of changing seas, and reflecting on the timeless lessons these travelers of the ocean have to teach us. For now, rest in the knowledge that waves connect us to the past, to the planet, to the vast forces that shape our world. They have been here long before us, and they will continue long after, rolling endlessly toward shore, carrying their ancient energy, singing their eternal song. All is well. All flows together. All is part of the rhythm. Dear traveler, to the final part of our journey through the world of ocean waves. We've traveled from the birth of waves in distant storms to their breaking on shores, from hidden internal waves to the ways humans have harnessed and been inspired by wave motion. Now, let's gently explore what waves mean for our changing world, and the timeless wisdom they offer us. Let's take this last peaceful walk along the shore together. As we move deeper into the 21st century, our relationship with ocean waves is entering a new chapter, one shaped by rising sea levels, changing storm patterns, and our growing understanding of how intimately waves are connected to Earth's climate system. Global sea levels are rising as the planet warms, currently at a rate of about 3.3 millimeters per year, roughly the thickness of 2 pennies stacked together. This might not sound like much, but it's accelerating, and even small changes in average sea level can have dramatic effects on coastal wave impacts. When waves arrive at a coast where sea level has risen even by a few centimeters, those waves can reach farther inland, their energy delivered to areas that were previously safe from wave action. The relationship between sea level rise and wave impact is not simply additive, it's multiplicative. A wave breaking on a beach at higher water level doesn't just reach a bit farther, it reaches exponentially farther up a gently sloping beach. Areas that experienced wave action during storms once every few decades may now experience it every few years, or even annually. Coastal communities are discovering that infrastructure built with adequate setback from historical wave reach is now vulnerable. This phenomenon became tragically clear during Hurricane Sandy in 2012, which struck the northeastern United States. While Sandy was a powerful storm, it wasn't unprecedented in terms of wind speed or wave height. But it arrived at a time when sea level along the New Jersey and New York coasts had risen by about a foot compared to a century earlier. That additional foot of sea level meant that Sandy's storm surge and waves reached areas that had been safe during similar storms in the past, causing an estimated $65 billion in damage. Scientists project that global average sea level will rise by somewhere between 0.3 and 1 meter by 2100, depending on how much greenhouse gas emissions are reduced. But in some locations, particularly where land is also subsiding, the relative sea level rise could be much greater. These rising seas will fundamentally change how waves interact with coasts, requiring extensive adaptation in coastal management and infrastructure. Climate change is also affecting the waves themselves, not just the sea level they ride upon. As global temperatures rise, atmospheric circulation patterns are shifting, which changes wind patterns over the oceans. These changing winds are, in turn, altering wave climates, the statistical patterns of wave heights and directions that characterize different ocean regions. Research published in the journal Nature in 2019 analyzed wave measurements from buoys and satellite observations spanning more than 30 years. The study found that wave heights in the Southern Ocean, the vast ocean surrounding Antarctica, have been increasing at a rate of about 1 centimeter per year since the 1980s. This might seem small, but over decades it adds up. The researchers linked this trend to strengthening winds in the Southern Ocean, which are themselves connected to climate change. Not all changes are toward bigger waves. In some regions, particularly parts of the North Atlantic, average wave heights may actually be decreasing slightly. But more concerning than changes in average wave height are changes in wave extremes, the frequency and intensity of the largest waves. Some climate models suggest that the most extreme wave events may become more common in certain regions as storm patterns shift, even if average wave conditions don't change dramatically. Understanding these changing wave climates has become crucial for coastal planning and for industries that operate at sea. Offshore wind farms, oil and gas platforms, shipping routes, and coastal infrastructure must all be designed to withstand not just today's wave conditions, but the wave conditions expected over the decades of their operational lifetime. Engineers now routinely incorporate climate change projections into their design criteria, acknowledging that the past is no longer a reliable guide to the future. Beyond these practical concerns, there's a deeper question. What happens to coastal ecosystems as wave conditions and sea levels change? Many coastal habitats, mangrove forests, salt marshes, coral reefs, kelp forests, have evolved under specific wave energy regimes. They're adapted to particular patterns of wave exposure, sediment movement, and disturbance frequency. Coral reefs, for example, are both shaped by and protective against waves. Healthy coral reefs dissipate up to 97% of wave energy before waves reach the shore, providing natural coastal protection far more effective than most engineered structures. The complex three-dimensional structure of the reef causes waves to break offshore, protecting beaches and coastal communities. But coral reefs are severely threatened by climate change, both from ocean warming that causes coral bleaching and from ocean acidification that makes it harder for corals to build their calcium carbonate skeletons. When reefs degrade, their ability to dissipate wave energy declines. The waves that once broke on healthy reefs now reach the shore with greater energy, increasing coastal erosion and flooding. Communities that have enjoyed natural protection from reefs for generations suddenly find themselves vulnerable. This has led to growing interest in reef restoration not just for biodiversity conservation, but as a coastal protection strategy. Organizations and governments are investing in reef restoration projects, growing and transplanting corals, with the explicit goal of rebuilding the wave-breaking function of degraded reefs. Similarly, coastal wetlands, salt marshes and mangrove forests provide wave attenuation, slowing waves and reducing their height before they reach developed areas. These ecosystems are themselves threatened by sea level rise, pollution, and development, but there's growing recognition of their value for coastal protection. Some communities are now removing seawalls and restoring wetlands, working with natural systems rather than against them, an approach called living shorelines that acknowledges the protective role that natural ecosystems play in managing wave energy. The science of how waves interact with these natural systems has advanced considerably in recent decades. Researchers have developed detailed models of wave attenuation through vegetation, measuring how effectively different types of plants reduce wave energy based on their stem density, height, and flexibility. This research is helping coastal managers design restoration projects that maximize both ecological value and coastal protection. As we look to the future, one of the most intriguing frontiers in wave science involves understanding and predicting extreme events. While we can forecast general wave conditions fairly well, predicting that a storm will generate large waves in a certain area days in advance, predicting specific rogue waves or the exact timing and location of maximum wave heights remains challenging. New technologies are helping. Networks of high-frequency radar systems can now map ocean surface currents and wave patterns in real time over large coastal areas. satellite remote sensing provides global wave observations. Machine learning algorithms are being trained on decades of wave data to identify patterns that precede extreme events. These tools are gradually improving our ability to forecast not just average conditions but specific hazards. One particularly promising development is the operational forecasting of wave run-up, how high waves will reach on a beach during a storm. This is more complex than simply predicting offshore wave height, because run-up depends on the interaction between waves, beach slope, beach composition, and often the presence of coastal structures. But accurate run-up forecasts can guide evacuation decisions and help coastal residents know specifically which properties are at risk during particular storms. The European Centre for Medium-Range Weather Forecasts now produces global wave forecasts extending 10 days into the future, with reasonable accuracy out to about 7 days. These forecasts help ships route around dangerous seas, allow coastal communities to prepare for incoming swells, and assist emergency managers in planning for storm impacts. The forecasts are constantly improving as models become more sophisticated and as more observational data becomes available to validate and refine them. Yet for all our scientific progress, waves retain an element of mystery and unpredictability. The ocean surface is one of the most complex systems in nature, a chaotic interface between fluid atmosphere and fluid ocean, influenced by wind, current, tide, and seafloor, with energy cascading across scales from ocean basin swells hundreds of meters long down to capillary ripples millimeters across. We understand the fundamental physics, but the details of how these processes interact to create the specific wave you see at a specific moment remains partially beyond our predictive reach. And perhaps that's as it should be. Perhaps waves should retain some of their mystery, some of their capacity to surprise and humble us. They remind us that nature is not fully controllable, not entirely predictable, not ours to command. Waves have been shaping coastlines for billions of years, long before our species existed, and they'll continue their work long after we're gone. And so we come to the end of our journey together tonight. We've traveled from the first breath of wind across calm water to the complex future of waves in a changing climate. We've explored 100 facts woven into a single story, the story of how waves are born, how they travel, how they break, how they shape our world and our lives. But more than facts, I hope you've found in this journey a sense of connection, to the ocean, to the planet, to the vast forces that make our world beautiful and dynamic. Waves are more than physics, more than energy moving through water. They're a reminder of rhythm, of cycles, of constant change that somehow adds up to stability. Think about this: every wave that has ever broken on every shore was once energy from the sun, heating the atmosphere unevenly, creating winds. Those winds touched water, transferring their energy to waves. Those waves traveled, sometimes for thousands of miles, carrying that solar energy across the ocean. And when the wave finally broke, that energy, originally from the sun, transformed through air and water, was released, doing the work of moving sand, shaping coastlines, creating the beaches where you might walk on a summer day. It's all connected. Sun to wind, wind to wave, wave to shore. Energy flowing through systems, never created or destroyed, only transformed and transferred. And you are part of this flow, made of atoms forged in stars, living on a planet shaped by waves, breathing air whose composition is influenced by wave-driven ocean mixing. As you drift towards sleep tonight, Let yourself be carried by the rhythm of waves. Imagine gentle swells rolling endlessly across a peaceful ocean. Feel yourself rising and falling with that ancient motion, safe and supported, rocked by forces that have cradled this planet for billions of years. Waves teach us about persistence. They never stop, never give up, always return. They teach us about resilience. No matter how they break, the ocean always sends another wave. They teach us about change. No two waves are exactly alike, yet all are recognizably waves. And they teach us about peace, that sometimes the most powerful force is also the most soothing, the most constant. The waves will still be rolling tomorrow, and the day after, and the day after that. They rolled yesterday, and the day before, and they'll roll for billions of years to come. There's comfort in that constancy, security in that endless rhythm. So rest now, dear traveler. Our journey is complete. You've learned about waves from their gentlest ripples to their mightiest tsunamis, from their hidden internal journeys to their visible breaking on shores, from ancient navigators reading swells to modern engineers harnessing wave power. But most importantly, I hope you've reconnected with something essential, the soothing, eternal rhythm of the ocean. That rhythm is always there, whether you're near the coast or far inland, whether you're awake or asleep. The waves keep rolling. The ocean keeps breathing. And you are part of it all. Thank you for joining me on this journey through calm science nights. May your sleep be deep and peaceful, your dreams as gentle as waves on a calm summer evening. The ocean whispers its ancient lullaby. The waves roll on. And all is well. Good night.